Firewalls and content filters deployed by enterprise networks and internet service providers are suddenly failing to catch traffic from the world's largest platforms. Data from YouTube, Instagram, and Facebook glides right past inspection checkpoints. Network administrators trying to enforce corporate data policies and state-level censors attempting to block unauthorized content are finding their control mechanisms bypassed. They cannot see what the traffic is, where exactly it is going, or how to stop it without breaking the network. Historically, these checkpoints relied on deep packet inspection, or DPI. DPI is a method of examining the data part of a computer network packet as it passes an inspection point, searching for protocol non-compliance or specific criteria to decide whether the packet can pass. To work, DPI needs readable metadata attached to the traffic. That metadata is vanishing because of the transition to HTTP3 and its underlying transport protocol, QUIC. QUIC is a transport layer network protocol designed by Google to accelerate web traffic by reducing connection times, while HTTP3 is the newest version of the hypertext transfer protocol that uses QUIC to send web data. By encrypting almost all connection metadata by default, this new standard blinds the systems that rely on reading packet headers to enforce rules. Deterministic network visibility, the ability to look at a packet and know exactly what application it belongs to, is broken. This is an immediate operational reality. Over 75% of Meta's total internet traffic, primarily from Facebook and Instagram, now uses QUIC and HTTP3. Google routes the vast majority of its Chrome and YouTube traffic through the same protocol. For security operations, this massive migration creates a severe blind spot for standard intrusion detection systems. An intrusion detection system, or IDS, is a monitoring application that scans network traffic for suspicious activity and issues alerts when it discovers potential policy violations or cyber attacks. Consumer tech companies engineered these protocols to protect user privacy and prevent unauthorized surveillance. However, enterprise IT departments require visibility to stop data exfiltration, and internet service providers need to manage bandwidth and shape traffic loads. To understand how modern network security resolves this blind spot, we have to look under the hood of the QUIC architecture, see exactly how it breaks legacy inspection, and examine the blunt force tactics administrators are currently using to hold their networks together. The collision between protocols designed strictly for privacy and the reality of administrative control mandates means the old way of reading packets is obsolete. Network monitoring requires an entirely new approach. To see what changed, we look at the traditional setup. For decades, web traffic relied on the Transmission Control Protocol, or TCP. TCP is a connection-oriented communication standard that requires devices to perform a strict three-way handshake, exchanging SYN, SYN-ACK, and ACK packets to establish a rigid, verified connection pathway before any data is sent. Only after that pathway is built does the cryptographic setup begin, typically using Transport Layer Security, or TLS. TLS is a cryptographic protocol designed to provide communication security over a computer network. The client initiates this encryption by sending a client hello packet. Inside that client hello packet sits the server name indication, or SNI. SNI is an extension to the TLS protocol that transmits the exact hostname the client is trying to reach, like youtube.com, in plain, unencrypted text. Because the transport connection is completely separate from the cryptographic setup, the SNI is visible to anyone sitting between the client and the server. A legacy DPI engine simply intercepts the traffic, reads this exposed SNI, and checks the requested website against its blocklist database. If the hostname matches a banned site, the DPI engine executes a TCP reset attack. It fires a forged packet containing an RST flag to both the client and the server, tricking both machines into violently terminating the connection. This specific interception tactic formed the backbone of the Great Firewall of China's censorship engine for over a decade. Systems would mirror all outgoing international traffic, match the unencrypted hostnames, and automatically sever connections to platforms like Google and Facebook. Realizing that external parties could easily hijack and kill connections just by reading the plain-text greeting, software engineers at major tech firms had to rethink how the transport and encryption layers interact. Keeping the connection establishment separate from the security handshakes leaves the initial routing requests exposed. This structural vulnerability makes interception and censorship trivial to execute. To close this gap, QUIC abandons the rigid TCP model entirely and builds on top of the User Datagram Protocol, or UDP. UDP is a connectionless communications protocol that allows data packets to be transmitted in a continuous, rapid-fire stream without requiring prior communication or verified handshakes. By using UDP as its base, QUIC supports native multiplexing. Independent data streams can flow through the same connection simultaneously, meaning if one packet drops, the others continue without waiting. More importantly, QUIC collapses the setup process using a zero round-trip time, or zero-RTT cryptographic handshake. It merges the initial connection sequence and the security key exchange into a single simultaneous action. The critical consequence of this merged handshake is that the client hello and its vulnerable SNI data never travel in plaintext. They are sealed tightly inside an opaque TLS 1.3 cryptographic shell the exact moment they leave the client's device. When a legacy DPI engine attempts to intercept a modern QUIC packet, its scanner strikes the UDP stream and fails to penetrate. Instead of readable domain names, the inspection tool receives nothing but garbled cryptographic noise. Without the ability to read the server name indication, the middle box has no context. It cannot distinguish between a harmless web search, an enterprise file transfer, or a restricted high-definition video stream. Baking the encryption directly into the transport layer permanently blinds deterministic network defenses. Any system that relies on reading packet signatures to make routing decisions is effectively locked out. This creates an immediate operational crisis for enterprise IT departments. Firewall administrators are legally and operationally mandated to filter specific content, but they lack the tools to parse application traffic. The current brute force workaround involves configuring firewall rules to categorically block all outbound UDP traffic on ports 443 and 80. If the firewall cannot inspect the protocol, it simply refuses to let it pass. Mechanically, when the client application attempts to establish its preferred QUIC connection over UDP, the firewall drops the packets. The initial connection attempt fails. This forces the client browser into a protocol downgrade. Unable to use QUIC, the application automatically falls back to the older, inspectable TCP and HTTP2 stack to maintain internet access. With the traffic forced back onto the rigid TCP connection, legacy DPI engines can once again read the plaintext SNI in the client hello packet. Administrative control is temporarily restored. However, this workaround comes with a severe performance cost. By blocking QUIC, the network completely strips away HTTP3's low-latency delivery and multiplexing advantages, artificially slowing down every request made by the user. Intentionally degrading network performance just to maintain visibility is an unsustainable strategy. As the web continues to optimize for speed and encryption, forcing traffic backward breaks the architecture of modern applications. To solve the QUIC blind spot without breaking network performance, security firms are deploying Encrypted Traffic Intelligence. Encrypted Traffic Intelligence, or ETI, is a monitoring approach that uses machine learning to classify network flows without decrypting the payload. The core philosophy of ETI shifts the objective entirely. Instead of attempting to read encrypted packet metadata, the system analyzes the overall behavioral patterns of the packets as they move through the network. The system measures packet inter-arrival times, payload sizes, and throughput bursts from the opaque stream. These plotted metrics coalesce into a distinct geometric cluster. This statistical shape is compared against established wireframes to deduce exactly what application generated the data. This method is highly accurate because even heavily encrypted applications leak identifiable behavioral patterns. The encryption only hides the contents, not the physical delivery mechanics of the data itself. For example, a voice-over IP call generates a steady, symmetrical flow of small packets in both directions. In contrast, streaming a movie generates heavy, asymmetrical bursts of large packets, followed by brief silences as the video player buffers. The physics of data transmission guarantee that different applications behave differently on the wire. Regardless of how thick the cryptographic envelope is, the shape of the traffic reveals its purpose. Modern intrusion detection systems now apply these heuristics at scale, classifying and routing massive volumes of QUIC traffic without ever needing to decrypt the actual payloads. This provides critical cybersecurity benefits, identifying malicious command and control beacons hidden within encrypted data streams. Command and control, or C2, refers to a centralized server used by attackers to maintain communications with compromised devices within a target network. The protocol arms race is not over. As engineers continue to enhance data privacy and obscure traffic patterns, these statistical analysis models must continuously adapt to maintain accuracy and minimize false positives. This creates an endless feedback loop between privacy developers working to hide data streams and network security architects building increasingly sophisticated algorithms to expose them. Network inspection has evolved from simply reading plain text name tags on passing packets to applying the complex geometric shapes of encrypted data flows in real time. The era of deterministic signature-based blocking is over. As protocols like QUIC become the default standard of the internet, AI-driven behavioral fingerprinting is now the mandatory baseline for network defense.